Good afternoon, my YouTube viewers. It's Crystal here. I just want to give you a code review of something that I worked on last night and this morning, and it's concerning the Brier score. I've never heard of the Brier score before, but I heard of it yesterday when I was looking at a machine learning paper. And so when I was looking at this machine learning paper, they were talking about the Brier score. And since I've never heard of it, I thought I would research it. So we're going to talk about the Brier score. The Brier score is a strictly proper score function or strictly proper scoring rule that measures the accuracy of probabilistic predictions. For unidimensional predictions, it is strictly equivalent to the mean squared error as applied to predicted probabilities. The Brier score is applicable to tasks in which predictions must assign probabilities to a set of mutually exclusive discrete outcomes or classes. The set of possible outcomes can be either binary or categorical in nature, and the probabilities assigned to this set of outcomes must sum to 1, where each individual probability is in the range of 0 to 1. It was proposed by Glenn W. Brier. So the probability score can be thought of as a cost function, more precisely across all items, and then it gives you some statistical figures. But the Brier score measures the mean squared difference between the predicted probability assigned to the possible outcomes for item I and the actual outcome OI. Therefore, the lower the Brier score is for a set of predictions, the better the predictions are calibrated. Note that the Brier score, in its most common formulation, takes on a value between 0 and 1, since this is the square of the largest possible difference between a predicted probability, which must be between 0 and 1, and the actual outcome, which can take on values of only 0 or 1. In the original 1950 formulation of the Brier score, the range is double from 0 to 2. The Brier score is appropriate for binary and categorical outcomes that can be constructed as true or false, but it is inappropriate for ordinal variables which can take on 3 or more values. And then they give you the formula for the Brier score, the most common formulation for the Brier score, and it tells you how to formulate the Brier score. So if you want to know more about the Brier score, well, you can read about it on Wikipedia. And what we'll do now is we're going to actually talk about the Brier score because we're going to use the Ionosphere dataset, and I got the Ionosphere dataset from GitHub. Somebody had a GitHub account and they put it on GitHub, and so I took it from that. So the first thing you have to do is you have to make predictions, and then you have to predict on the probabilities. And then so what you're going to do is you're going to predict on the probabilities and then compare it to the actual values. And we're going to do that at the very end of the program. So the beginning of the program is going to be like any other machine learning program. And at the very end, we're going to talk about the Brier score. So the first thing we're going to do is we're going to import libraries. And I misspelled libraries. So we're going to import NumPy as NP to create your NumPy arrays. We're going to import pandas as PD to read in the data sets and convert them into data frames. And then we're also going to data process. We're going to import matplotlog.pyplot as PLT, so that's going to visualize your data, and then we're going to import Seaborn as SNS, so it's going to visualize the data statistically. And then what we're going to do is we're going to use pandas to read in the data frame. So we've used our pandas to read in the data frame. And we've got 351 rows by 35 columns. Check info. Fortunately, this is all a numeric data frame, so you don't have to do any encoding because it's all numeric. Now, it looked to me like it's already been standardized. That's what it looks to me like. So in this particular program, I didn't standardize it because it looks like it's already been standardized. Check to see if we had any null values. We didn't have any null values, so that's good. So we didn't have anything to impute. Now what I wanted to do, I wanted to check these integer values. You had a few integer values. And so we're going to check the number of unique values in the integer values. So for a column in data, if datacall.dtype equals int64, print call datacall.inUnique, so that's printing the number of unique values. If datacall.inUnique equals 1, we're going to drop it. You're going to toDrop.append call, print toDrop, and then data.drop toDrop axis equals 1, in place equals true, print data shape. So we had V1, V2 in class were integers, and so V1 in class had 2 unique values, and V2 had only 1 unique value. And since it had only 1 unique value, it wasn't needed, so we dropped V2, and so now instead of 35 columns of data, we have 34. And then the next thing you do is we're going to analyze the target. So target equals data.popClass, sns.dispplot, target, KD equals true. So you can see we've got 0 and 1, and there does actually look for it does actually have a class imbalance. So that means we're going to have to set up some class weights. Then I used Seaborn to create a heat map. And when I created a heat map, I could see by looking at the heat map that none of the columns were very highly correlated, so I didn't have to do anything about that. But if you want to know how highly correlated the columns are, you've got core, and that will tell you how highly correlated the columns are if you want to know that. And now what we're going to do is we're going to define our x and our y variables. So y is your target, x is data. We print x and y, the shape. So x is 351 rows by 33 columns, and y is 351 rows. So now what we do is we split our data set into training and validation sets. We use sklearn's train test split to do that. And so now we've got 315 rows for the training set and 36 rows for the validation set. And now what we're going to do is we're going to define our class weights using sklearn's. So weights equals class weight dot compute class weight equals balance, classes equals np dot unique y equals y dot values dot reshape -1, then weights equals dict zip np dot unique y weights. So you've got your weights as 0 is 1.39 and 1 is 0.78. Now what we're going to do is we're going to create a deep neural network. So we're going to go into TensorFlow, and you can see, and we're going to import the TensorFlow library and associated modules. And you can see that we're working on TensorFlow 2.12. Now what we're going to do is we're going to define the model. So the model equals keras.sequential, name equals Ionosphere, and then you're going to have your input model is X-train shape 1, and the name is input. Model.add layers is dense. We're going to have 50 neurons for the hidden layers. Activation is going to be reglue. We're going to have a dropout of 0.2, and then the final layer is going to be one output. And well, this final hidden layer is going to be activation equals switch, and then name equals layer 2, and then the final layer is going to be one neuron for the output, activation equals sigmoid, and name equals output. But one thing that you could do, because switch is related to sigmoid, but what you could do is you could try different activation functions to see if you could get your score to improve if you wanted to. So we could try reglue or try 10H, because there's a number of activation functions, but I think people tend to use reglue. But switch is for a binary classes, and if you want to use 10H or something like that, you can always give that a try and use what's going to give you the best output. So we do a summary of the model so you can see what the model looks like. So now what we're going to do is we're going to compile the model. The loss function is binary cross entropy. Optimizer equals atom, and metrics equals accuracy. My callbacks equals keras.callbacks.early stopping. Monitor valve loss. Patience equals 3. I'm going to change that to patience equals 25 to see if I can get the score to improve. So whenever I finish this code review, I'm going to change patience to 25 to see if I can get the score to improve. And I might make that 100. See what happens. So we're going to train the model, model.fit, x-train, y-train, epochs equals epochs, validation data equals val, x-val, y-val, verbose is 1, callbacks equals my callbacks, class weight equals weights. So that had early stopping at 2750 and at 94.44. And then we're going to plot a graph of the loss and the accuracy. So you can see the accuracy is 94.4. And then what we're going to do is we're going to evaluate it. And when we evaluate it, you see it's got an accuracy of 94.4. We're going to check our ypred prob equals model.predict xval. Ypred prob equals ypred prob flatten, and ypred prob, so you can see that that's the probabilities. And now ypred equals model.predict xval greater than 0.5 s type int 32, and it could be int 64 if you wanted it. Ypred equals ypred.flatten ypred. And so you can see it's a bunch of ones and zeros. And so we created a histogram. So you can see we have a class imbalance in this as well. So we're going to check the accuracy score against the yval and the ypred, and you can see it's 94. And we're going to check the confusion matrix. You can see we had 11 zeros and 2 ones that should have been 0, and we had 23 ones, so that was good. And then we're going to create a data frame that compares the actual values against the predicted values. And then now we're going to do the Brier score. Brier score equals np.mean y-pred prob minus y-val, and it's to the power of 2, so that's squared. And then so your answer is 0.049, and what you want is you want the reading to be as low as possible, because the lower the reading is, the better it's going to be. So it's pretty good. It's 0.04. So what we're going to do is we're going to run it again and see if we can improve the score by changing the early callbacks. And now we're just training it. It says 52 over 100, and it's still 94.4. And so it's 0.431. But what we could do, let's just see what happens, since it's a quick program. Let's just see what happens when we do a ReLU. Let's just see what happens when we do 10H. Nope, 10H makes it even worse. So 10H makes it even worse. Let's try swish again. So 10H made it worse. So 10H didn't improve it. Still 94.4. Let's just see what happens. Well, we could do both of them ReLU. See if it improves if both of them are ReLU. See what happens. Nope, it didn't improve when both of them were ReLU. So we tried ReLU, 10H, and swish, but it was 0.51 with both of them as ReLU. So let's go back here. So it increased with them ReLU. So let's try swish. Nope. Let's try it again. Try them with ReLU. Both of them is ReLU. Try both of them as being ReLU. So see, what you can do is you can experiment with different activation functions. But ReLU's not any good. ReLU's not any good. It's gone down, so try it with the original one. So the original one is 0.5, and then whenever I had originally done it, it was 0.4. But that's what we wanted to do. We wanted to have the Brier score and calculate the Brier score. And the reason why I wanted to calculate the Brier score is because I read about it in a paper, read about it in a paper, and I read about it in a paper, and obviously it's used in machine learning. I mean, I haven't seen it in machine learning, but it is used in machine learning. So I wanted to bring it up in machine learning. And I'm going to make a blog post about this and discuss it and discuss the Brier score further. So I thought, well, before I make this blog post, I'm going to do a code review. So thank you so much for watching my code review. Thank you so much to my subscribers for supporting my channel. If you like my channel, please like, subscribe, and share. And thank you again. If you want to be notified whenever I make a new video, please tap onto the bell button next to the subscribe button, and I'll notify you whenever I make a new video.